All right, so let's review. What did we talk about last time? So last time we talked about now we properly defined what a directional derivative is. When we're looking at these directional derivatives, it's helpful to always think of it this way, right? Like we have this plane x and y, and then we have this height z, and what like partial f over partial x is measuring is how quickly is the height increasing with respect to the x direction, right? What partial f over partial y is measuring is how quickly is the height increasing with respect to the y direction, right? And so now what we did is we said, okay, well, let's do like a mixture and have u be some combination of x and y. And then how should we define how quickly the height is changing in terms of that direction, right? And so we came up with a definition. We used a limit definition once to kind of see how it worked. And then we said, okay, well, that was great. So let's come up with a formula now for this using the things that we've already done. And in doing this formula, we came up with this sort of new vector, which is just all these like partial derivatives. And so our new sort of, so we define this gradient vector right here, which technically this should be, I mean, you can define it, but this is technically defined at a point. And so we'll try to make that distinction and put things like at P0 or something like that to make this distinction at times. I didn't do it here, but I think I did it other places later. It's a little bit tedious to write that. It's kind of assumed sometimes that it's at, for example, P0.
As opposed to being.
So like, I mean, you can just define it at any point, like just by just taking the partial derivatives and making a vector out of it.
Okay, well, I'm saying like, you're saying at P0, where else could it, like?
I mean, you evaluate functions at points.
Oh, okay.
I mean, it's like a vector value function itself.
I just thought you were implying that you could evaluate them along a line or something like that.
No, not really. I mean, yeah, that wouldn't really work, I don't think. Yeah, so we did some examples of this. So now our sort of our directional derivative is this gradient of f at P0 dotted with u. We did some examples, and one of the first things that we kind of like came across here is this idea is that if you draw like these level curves in the xy plane, so on these level curves, like f of xy is a constant value. So the height is not changing, right, on these level curves. So you would expect that this duf thing would be 0, right, for that reason on these level curves, because the height's not, because this is like measuring how quickly the height is changing along this direction, but along a level curve, the height is not changing at all, right? So it should be, so it makes sense why, like when theta, for example, is pi over 2, right, that it's 0, and it makes sense that these should actually be like perfectly like, if you make the tangent line here, like for example at this point, for example, you should have a 90-degree angle, a pi over 2 degree angle, right? It should be orthogonal, right, to these level curves, since it's constant along these level curves. Okay. Since the rate of change of the height is not increasing. So what we kind of like, so like the key takeaways here is that the derivative changes most quickly in the direction actually of the gradient. So if we set u equal to be parallel to the gradient, right, that's going to be where the function is changing, the height is changing the most rapidly. Right, which is also with the dot, yes. And then if you set it like, you know, a negative multiple of the gradient, it's going to be where it's decreasing the most, right? And if they're orthogonal, right, then you're going to get 0. So hopefully that kind of makes sense, like intuitively, at least. Let me make sure I'm recording again. All right, so we did some more examples. Let's see, we did gradients and tangents to level curves. So we also kind of came up with this idea that, what was it? What were we trying to do here? So in this situation, we had that f of xy was c, and I feel like we came up with the new, yeah, so we came up with, through doing this and kind of making these observations. So for example, when f of xy is c, the derivative, right, with respect to t, if we're along some smooth curve, is going to be 0. And so we can use that then to our advantage to like come up with, okay, so the gradient of f and dr over dt are going to be orthogonal. And you can kind of see that like in this picture. It makes sense why they would be orthogonal again, because it's constant along these f of x0, y0 is constant along these level curves again. So we're going to have this sort of like this pointing kind of in this orthogonal direction to the tangent line there. And that also gives us a way then to make the tangent line to a level curve, which is just going to be this sort of fx at x0, y0 times x minus x0 plus fy times y minus y0 equals 0. Will then give us this tangent line. We did an example of that. And then we talked about for these gradients, we talked about some of the rules that we have. And so basically it follows kind of like the product rule, the quotient rule, all the rules that we would expect a derivative type sort of object to satisfy. So now we're just we have a few more things to do in this section. And so this next page I kind of just redid and wrote a little more. So we're gonna kind of go to here now to functions of 3 variables. So we're just gonna extend this a little bit more here still. So if we have f of x, yep, y, z, differentiable function, and let's say we have a vector u here. So this is just some like u1, u2, u3, right? Then we have that, we're going to have that the gradient of f here. In this case, we're going to have 3 different things. We're going to have partial f, partial x, partial f, partial y, partial f, partial z. And again, we're going to have that d u f here is going to be this derivative in the direction of u. It's going to be delta f dot u, right? So this is going to be delta f over delta x u1 plus delta f over delta x u2 plus delta y, delta f over delta z u3. And this is also, we could also write this as the magnitude of f, the magnitude of u, cosine theta, but u is a normal vector, right? So this is just the magnitude of f times cosine theta, since u is a unit vector. Okay, so let's do an example of this right here. So let's see, find the derivative of f of x equals x cubed minus xy squared minus z at this point in the direction b equals 2 minus 3 comma 6. So in what direction does f change most rapidly at p0? Okay, that's a part B. So we'll do part A, kind of like this is part A first, we'll say. Okay, so for part A, okay, so the first thing to remember, like whenever you're doing this, right, and you have this in the direction of, you have to make it into a unit vector first to get like the correct rate of change. So the very first thing we're going to do here is just calculate the magnitude of v here. And so the magnitude of v is going to be the square root of see, 4 plus 9 plus 36. Does that make a whole number? Yes, 49, so 7, right? So now we have that u.
Oh, you mean the square root.
Yeah. So that gives us that u here is going to be v over the magnitude of v, which is going to give us 2 over 7 minus 3 over 7, 6 over 7. Okay. So now that we have that, now we're just going to calculate the partial derivatives at these points. So fx at let's say we'll use this notation, I guess. At what is it? At 1, 1, 0 is going to be 3x squared minus y squared at 1, 1, 0, which is going to be 2. Let's see what else. Fy at 1, 1, 0 is going to be what? 2yx minus 2yx?
Yeah.
At 1, 1, 0, which is going to be minus 2. And fz at 1, 1, 0 is going to be just minus 1. All right, so with that, so let's see, so delta f, so d u f here at 1, 1, 0 is going to be the gradient of f at 1, 1, 0 dotted with u, right? And so that's going to be, what do we get? 2 minus 2 minus 1 dot. What do we get for u? 2, 1. I'm going to take out that 1/7. 2. Yeah, sorry. 2 minus 2 minus 1, right? And then we had 2 minus 3, 6. So it's going to be so this ends up being, I think, 4 over 7 in the end. All right, B. So in what directions does f change most rapidly? So it changed, so we can just answer this from that previous remark that we made, changes most rapidly in the directions of delta f or minus delta f. And the rates of change in these directions are plus or minus the magnitude of delta f at what? At 1, 1, 0, which is plus or minus the square root of, so we already calculated this, right? This is the square root of 2 squared plus 2 squared plus 1. So I got that just from, because the gradient, right, is we found the gradient to be 2 minus 2, 1 at 1, 1, 0. So that's going to be equal to 3, right? So in the direction of u, we had a change of 4/7. The largest direction of change right, is in the direction of the gradient, and it's 3. Plus or minus 3, so yes.
Oh, because you, okay.
Wait, how do
I know
you get
because
to negative
three.
2 negative 1?
How do I get, for which part? Here?
Yeah. No, down below. The
2 squared.
on your, how'd you get the
This?
2 negative 2? Yeah.
So the delta F at 1, 1, 0, we calculate each component. We got 2 right here, and then minus 2, and then minus 1. So this gradient of F thing is, what should I write? Let's see. Right, the gradient of F is Fx, Fy, Fz, these partial derivatives right here. So it's just the vector of the partial derivatives.
Oh, so you just plug in.
And I evaluated those. I evaluated them at 1, 1, 0.
Okay.
So I just did them each independently right here. So like, for example, if we were just to write the gradient of F for this problem, like the gradient of F would be, like if for any point, it would be like 3x squared minus y squared minus 2yx minus 1, for example. But then we just evaluated that at 1, 1, 0. What?
Oh, this just seems like a quick summary of what we did yesterday.
Yeah, it was a lot to take in yesterday, so I wanted
Okay.
to go over
No,
some
I'm
stuff
just saying,
again.
it's been nice to look back on studying.
Yeah. So one more thing that will kind of lead us into the next section now. So the chain rule for paths now. So let's say if, I need a little more space here. So if, let's say we have a vector now, r of t, we have a vector valued function, which is a smooth path C. So this will just be some x of t, y of t, all these, the x, y, and z here just depend on t here. Then according to the chain rule here, and now we're setting w equal to f of r of t. So that just means that that f now is becoming a function of time instead of x, y, and z, essentially, right? Then the chain rule told us that the way that we go about taking the derivative here, dw over dt, is going to be partial w over partial x, dx over dt plus partial w over partial y, dy over dt plus partial w over partial z, dz over dt. That was from 13.4. We went through these various chain rule things. And so, but again, like what you'll start to notice with a lot of these things is that we can kind of rewrite this as a dot product again, right? So we could think of we can think, for example, of this dx over dt, dy over dt, right? So r prime of t, for example, is dx over dt, dy over dt, dz over dt, and delta f is going to be, right, partial w over partial x, partial w, wait, do I want to use f here, or, yeah, that's fine, because we said w is f of r of t, right? So partial w over partial y and partial w over partial z. So what's the difference here? Like, is that like, when we did like r of t was already a vector, right? And when we did the derivative and got these d's, like that's again a vector. Now f, on the other hand, was originally not a vector, right? It was like its output was just one output. I mean, it took in a vector quantity, but it just outputs one vector. But now delta f is again a vector, right? So, okay, so hopefully that makes, so we can rewrite this whole thing right here as being, instead of w, we could write this as d over dt. So we can rewrite this as d over dt f of r of t is going to be delta f evaluated at r of t. And then, right, and that's going to be the partial w of partial x, partial w, partial y, partial w, partial t, except after we do these partial derivatives, we plug back in whatever r of t is, whatever x of t is, y of t, z of t. So it's at r of t, right? And then dotted with r dot prime of t. So let's keep that kind of equation in mind here for the this next section, because I believe this will kind of come up right.
Wait,
R prime, yes, because we have,
oh, dotted with R, okay.
yeah, it's a dotted with r prime, because r prime is that and delta f is that.
When you said R dot prime, I thought you meant like you use dot notation at first, so that confused me.
Oh, yeah, we're not using, yeah, that's, using dot notation is more for, I forgot what we were using that for. Oh yeah, we started using that when we were doing polar coordinates, yeah. So let's just rewrite this out again. What did we just find? That's going to kind of come now into this next. Did I write that way? Yeah. So we found, I'm just going to rewrite that so that we kind of have it here. So d over dt f of r of t. We found that we can kind of rewrite this here as delta f at r of t dotted with r prime of t. Okay. So so now let's assume that we are actually like on a level surface of this f of x, y, z. Because with level surfaces in 3 variables, we can at least kind of visualize what it looks like. You know, remember that f of x, y, z like is technically like a something in 4 space, at least. Like the graph of f of x, y, z would be something in 4 space. It would be like a volume in 4 space is what it would be. But if we like set it equal to c, then we can at least make 3-dimensional level volume surfaces.
Is it essentially the equivalent of the contour graph for f of x,
Yes,
y?
yes,
Okay.
yes. Or a level surface, we would call it. But yeah, yeah. The contours are like on the graph itself.
Okay.
The level surface is like the plot in the 3 space.
Okay.
All right. So since, okay, so what's going to happen here now? So since f of x, y is constant, right? We're going to have that d over dt f of r of t is equal to what? 0, right? Good, right? So what does that mean then for us? That means that that this dot product, these things have to be orthogonal, right? So that means that the gradient of f here is orthogonal. Since now we're not even like really doing this at a point, like this is just always true. This is orthogonal to the velocity r prime of t. Okay, so with that being known, let's see, so how can we kind of now use that? So let's restrict our attention to curves that pass through a point P0 now. So all velocity vectors at P0 are orthogonal to the gradient of f at P0. So the curves, tangent lines all lie in the plane through P0, normal to the gradient of f. All right, so since we have this since all the velocity vectors, right, all these sort of tangent lines, right, what this is saying is that all these tangent lines, right, are normal to the gradient of f And that gives us a way to make a plane, right? Does that make sense? Like it gives us, right? So like a plane, you know, right, you just take the normal vector, which is gradient f in this situation, and you dot it with p0, p, where p is like x, y, z, and p0 is just like the point on the plane. Okay. So okay, so now we can now kind of like properly now define the tangent plane. So the tangent plane at the point p0, x0, y0, z0 on the level surface f of x, y equals c of a differential function f is the plane through p0 normal to delta f restricted to p0. So the normal line of the surface at p0 is the line through p0 parallel to delta f. All right, so we've kind of been through this before, but let's write down what these equations are going to be. So the tangent plane here is going to be then the gradient of f at p0 dotted with the vector p0p that we could form, right, is equal to 0, or in short, or maybe a better way to write this here is fx at the point p0, evaluate at p0, right, times x minus x0 plus fy evaluated at p0, z minus z0 plus fz at p0. Wait, what did I do? This one should be z minus z0, but I have something else wrong there. That should be y minus y0, right? Right, and so that's just expressing that dot product now. And the normal line, okay, so to make the actual line now, right, so that line, right, is going to be parallel to the gradient, right, since that gradient is like sticking upwards. So here's kind of like a picture. I didn't get a chance to put pictures this time, but here's like a picture. Here's like a surface f of xy equals c, and then here's like this sort of tangent plane, and then you have this gradient f just sticking like straight up from it. And yeah, and so all of these are like these tangent lines that are tangent to the, that make, yeah, that, yeah, this great, say again? Yes, this gradient f is evaluated. It's like this vector fx at p0, fy at p0, fz at p0, right? So yeah, this gradient, again, yeah, this gradient f here is f, in this notation, fx, fy, fz, if that was confusing. All right, so, and then the normal line, okay, so to make the line, well, we just make a line. We'll use parametric equations for this, but x is x0 plus fx at p0 times t, and y is, so the same thing with the rest. Y is y0 plus fy at p0 t, and z is z0 plus fz at p0 times t, or written more succinctly, this is going to be this normal line. I don't know if I should call it n, maybe. N is equal to, we'll call it R0 for x, y, z, maybe, for x0, y0, z0, and then the the gradient of f. Yeah, I'm trying to decide if I want to write, yeah, we'll stick to this notation at p0, we'll say, like that, and then times t, right? Or, so this is like in vector notation, where when I'm writing this, R0 here is x0, y0, z0. So that's kind of what I meant there with that. All right, so let's do an example of this. find the tangent plane and normal line to the level surface f of x, y. I think I meant this to be 9, not that it matters really. F of x, x squared plus y squared plus z. It matters to make this 1, 2, 4 work though. All right, so let's see. Let's just first start by calculating the gradient of f here. So the gradient of f is going to be 2x, 2y, comma 1 for the derivative of z. So the gradient of f at 1, 2, 4 then is going to be 2, 4, 1, right? 2, 4, 1. Okay, so therefore the equation for the plane is going to be 2 times and then x minus 1, right, plus 4 times, so we're going to use that 2 now, so y minus 2, and then plus z times plus 1 times z minus 1 equals 0. Z, what am I doing wrong? Yes, sorry, I don't know, where did I get 1 from? Both from the gradient, whoops, yes. Z minus 4, thank you, equals 0. Or if we were to simplify this down, it would be like 2x plus 4y plus z equals 14. Okay, so the 9. The 9 actually is only playing a role to make this point actually work for the equation in this situation. And so since the derivative of a constant 0, it's not really playing a role anywhere in this. So like if you plug in 1, 2, and 4 into the original equation, yeah, for that. Another example here.
No, we need the normal line as well.
Oh yeah, normal line. So the normal line then is going to be just if we write it, does it ask it for? We'll just write it in parametric here. Oh, x is going to be, so our point is, so we have 1 plus and then 2, right? So 2t, y equals 2 plus 4t, z equals 4 plus yep, 4 plus t. Yep. All right, so in this example here, we did it when f of x comma y is c. So that the situation kind of comes up sometimes, but other situations, they like define z explicitly, and like z is f of x, y. And that makes like a surface this time in 3 space. So it's generally the same idea, but a little bit different. And so we just have to slightly modify kind of like this whole derivation just a little bit to take care of that situation. And really all it's going to do is it's going to just make this fz sort of not exist in a sense, right? So we're going to do that now. So similarly, we can slightly modify the results above to find an equation for the plane tangent to a smooth surface z equals f of x, y at a point p0, x0, y0, where this time z0 is f of x0, y0. So how are we going to rewrite this? So we're going to rewrite z equals f of x y as f of x y minus z equals 0, right? So now, and we're thinking of this as being, I don't know, some f bar of x, y, z now, right? So this f bar now we can treat exactly how we treated the previous case. It's just that now we're just gonna have some parts that depend only on x and y and then subtracting z. All right, so if we do this, then, so maybe we'll call this, let's call this capital F actually, capital F, right? So if we actually go through and compute these things, so partial fx, right, is going to be partial over partial x this time, calculating the gradient, the partial derivatives of f of x, y minus z, right? And so this is still going to be little fx like last time. So it's not, so that's not going to change in this equation. Capital Fy is going to be partial over partial y, f of x, y minus z, which is little fy from that equation last time. But then, you know, so the only thing that's going to change is capital Fz, right, is going to be partial over partial z of f of x, y minus z, right? And so this time, we're not going to have an fz term. We're just going to change that fz term just to minus 1, right? Because the derivative of minus z is minus 1. So what this is saying is that we're going to take this equation that we came up with, and the only difference here is that we're going to change this fz at p0 to always be minus 1, right, in this situation, right? So, so we can write this. So the tangent line to the surface z goes f of xy at x0, y0, f of x0, y0. The plane tangent to the surface of a differentiable function at the point z equals fy, at the point p0, sorry, x0, y0, y0, z0. We'll say that this is, okay, we're going to rewrite this as x0, y0, f of x0, y0, and think of it like that, right? And then this is going to be just basically what we wrote down last time, fx at x0, y0. Instead of writing p0, we'll just write it like that instead. So it means the same thing. X minus x0 plus fy x0, y0 times y minus y0. See a y here. And then, but then we said that this fz is going to be minus 1, so minus z minus z0 equals 0. So the only difference here is this slight term that we have, like one less term to compute. That's just going to be minus 1. All right, so example of this. Find the plane tangent to the surface z equals x cosine y minus y e to the x at 0, 0, 0. All right, so what I'll do, we just need to calculate fx at 0, 0 and fy at 0, 0 here, right? So we'll just do that real quick. So fx here is going to be what? Cosine y minus y to the x, right? So fx at 0, 0 is going to be cosine of 0, which is 1, right? And then fy is going to be minus x sine y minus e to the x, right? So fy at 0, 0 is going to be minus e to the 0, which is minus 1. I believe that's all we had to really calculate, right? So this is going to be, so the tangent plane here is going to be 1 times x minus 0 plus a minus 1 times y minus 0. And then we always just add this minus z minus 0 equals 0, or x minus y minus z equals 0. Gives us the tangent plane at 0, 0, 0. Tangent plane, let's say, at 0, 0, 0. And so this is kind of like, so again, just to make sure that the visualization is there, right? So we're having the surface, like in that previous example, x squared plus y squared plus z minus 9 equals 0. And we are finding the equation for this. And the normal line is sticking straight out, right? And the tangent plane is this tangent, this red tangent plane right there. Okay. All right, so slightly more complicated example. Let's see the surfaces here. So let's have these surfaces f of x. This is going to kind of bring in some other stuff from back in chapter 11. That was also probably on the tests. X squared plus y squared minus 2. So if you're not familiar, if we set this equal to 0, we are gonna get a cylinder, because this is gonna make a circle, and if we set it equal to 0, it can, in the z direction, it can extend infinitely in either direction. This is a 2, not a z. Okay. So this is a cylinder, right? And let's have g of x, y, z be x plus z minus 4. And so this one is defining, if we set this equal to 0, again, y can run freely. So this is going to make a plane, right? And so this meets in an ellipse E. So why does this meet ellipse E? Well, think of it this way, like here's the cylinder x squared plus y squared minus 2. And then here is the plane x plus z minus 4. And when they intersect, it's going to make a cylinder, right? So ellipse, yes. Yeah, right. So find parametric equations for the line tangent to E. So so E being this ellipse at the point P0, 1, 1, 3. Okay, so what do we know? Okay, so if we want to find this tangent line at E, which is the intersection of these two things, what do we know? So one of the things that we know, right, is that the tangent, we just talked about this, all tangent on this previous problem, right? Like in this example, right? Here is all tangent lines are in this plane, right? And each tangent line in this plane is orthogonal to this normal line, which is the gradient, I mean, which is the, and this normal line we talked about, right, is in the direction, right, of the gradient, fx, fy, fz, right? So, so we know that the tangent line, right, is orthogonal, right, to and if we look at the intersection of these, it's to both delta f and delta g, right, at P0 here, right? So, so what this is going to amount to then, right, to find this intersection line, well, there was an equation that, so therefore tangent line is parallel to what? So I'm trying to quiz you guys on something back in chapter 11, right? If you have, so if we made the plane, right, like, so delta f at P0, right, is orthogonal to the plane, the tangent plane for f, right, for the cylinder, and also orthogonal to the tangent line of left. So these are like kind of like our normal vectors, for each plane, right? And we're essentially intersecting two tangent planes, right? So the tangent plane for the plane is just the plane itself, right? But the tangent line for the cylinder is a little bit different. So what was that formula that we used for the intersection of two planes? Cross product. There we go, right? Yeah, cross product, right? So the tangent line then is parallel, yeah, to the gradient of f cross the gradient of g. There we go. All right. So we have to calculate these all this stuff. So yes, at p0. We should probably keep saying that. So the components of v and the coordinates of p0, right? So p0 also, notice that 113, right, is going to work for both equations. So we already have so we're already in a sense given, right, that, you know, like 113, we should just double check, right? But yeah, that works. 1 plus 1 is -2, 1 plus 3 minus 4, right? Okay, so we already have this point to make this line, so we just need to calculate this vector that it's going in the direction of. So the gradient of f here is going to be 2x, 2, is this how I want to do this? Yes, 2y 0. So the gradient of f at 1, 1, 3 is going to be 2, 2, 0, and the gradient of g at is just going to be the same everywhere. 1, 1, 3 is just going to be the normal vector, which is 1, because it's 1x, and then 0y and 1, right? So our v then, right, is going to be what do we say? We said v is delta f cross delta g at 1, 1, 0, 1, 1, 3, right? And so that's going to be this whole I, J, K, 2, 2, 0, 1, 0, 1. And if we calculate this out, we're not going to do it right now, but we're going to get 2 minus 2 minus 2 if we calculate this out, which I assume that we all can kind of do this by this point. So, and then ask for the parametric equations. So for the parametric equations, we're going to have x is equal to, what's our original point? 1 here, right? So 1 plus, and then here we got a 2, so 2t, y is equal to 1 plus a minus 2t, and then z is equal to 3 plus a minus 2 times t. All right, so I think that is good. And now I needed to decide if I want to go through the rest of this section or not next time, or to skip the section after this. So, yeah. Well, after this, they're doing a bunch of approximation stuff, and I don't know if I want to do approximations. I don't know. Linear approximations. I feel like it's important for like engineers maybe, so I should probably do it. We're getting close to the optimization stuff, which is fun. Optimization stuff.
On Friday, you want me to do anything before?
Just remind me to, if I don't, I'm starting to post the lectures now, so just if I don't, remind me.
Okay.
Yeah, and there will be homework assignments up like very soon, so be ready for those. Hey, how you doing?
So if we were to set f of x, y, z and g of x, y, z equal to each other,
Mm-hmm. Oh, you're asking for a different way to solve the problem, right? Yes, there is more than one way to do this. You could probably even take this and you could probably even turn this into a Coughlin problem. Let's see, could you? If you set these equal, so if you set these equal to each other, what would happen? You would have to replace x with 4 minus z, right? Put it into here, and then you could just work. Then you could just use the equation for the tangent, and then you could do like implicit differentiation. I don't know. It would get messy though. I mean, yeah, you could definitely do it that way though. Yeah. But it often is like a little bit easier to do it this way, I guess. Maybe. I don't know.
Maybe.
Yeah. But yeah, good question though. Yeah. Have a good one. Is there anything else going okay? Okay, cool.